In the early hours of last Saturday, telescopes pointed at the interstellar object 3I/Atlas recorded something no astronomical model could predict. The celestial body's velocity dropped abruptly to near zero. For exactly 48 hours, that cosmic traveler, which had been crossing the solar system at tens of thousands of kilometers per hour, simply stopped. Observatories on 3 continents confirmed the anomaly almost simultaneously, and the scientific community went on high alert. Interstellar objects don't take breaks. They don't lock up. They don't freeze in the vacuum of space without a clear physical reason. And that reason, so far, no one has been able to find. The first detection came from the automated tracking system at La Silla Observatory in Chile. The algorithms identified a drastic drop in the angular displacements of 3I/Atlas between 2 consecutive images. Minutes later, telescopes in Hawaii and Australia confirmed the object had stopped its displacement relative to the stellar background. What should have been a constant luminous trail transformed into a fixed point, as if someone had pressed the pause button on a cosmic simulation. During the following 48 hours, hundreds of measurements were taken. All pointed to the same result: virtually null movement. This behavior is absolutely unprecedented. Comets can decelerate by losing mass through sublimation. Asteroids can undergo subtle changes due to thermal effects, but no interstellar object has ever registered such an abrupt and prolonged stop. While the telescopes monitored the phenomenon, spectroscopy instruments continued operating. And that's when the situation became even more baffling. The brightness of 3I/Atlas remained stable throughout the entire period of immobility. There were no signs of gas ejection, material jets, or any type of surface activity that could explain a sudden loss of momentum. The light curve didn't oscillate, the spectrum showed no significant changes, and the absence of any sign of fragmentation or collision made the event even more enigmatic. Radial velocity data, obtained through Doppler analysis, showed a sudden and inexplicable change. The object simply stopped moving relative to our reference frame. All known dynamic models, which consider gravity, solar radiation pressure, rotation effects, and even magnetic interactions, failed to predict or explain this behavior. Initial hypotheses emerged quickly, but none withstood rigorous scrutiny. Some researchers suggested that 3I/Atlas might have crossed through an exceptionally dense region of interstellar dust, creating a kind of aerodynamic break. The problem is that there's no evidence of such a cloud near the object's trajectory, and even if there were, the density necessary to cause such drastic deceleration would be detectable by other means. Another possibility raised was that of a momentary rotational lock, perhaps caused by an internal redistribution of mass. However, solid objects don't exhibit this type of behavior without visible external manifestations. And then there are the more daring theories, which some scientists prefer not to completely dismiss: a gravitational interaction with an as-yet undetected body, a temporary capture event by a local spacetime anomaly, or even physical phenomena we don't yet fully understand. Inside NASA, the event generated a wave of perplexity. Orbital dynamics teams ran simulations repeatedly, adjusting parameters, testing extreme scenarios, but none managed to replicate what was observed. The data defies everything we know about celestial mechanics applied to objects of this nature. The lack of a coherent physical explanation led the agency to issue a technical alert to observatories around the world, requesting independent confirmations and additional measurements. Meanwhile, theoretical astrophysics research groups began reviewing fundamental models, questioning whether there are gaps in our understanding of how interstellar bodies interact with the solar system environment. The search for data from other instruments, infrared observation satellites, X-ray detectors, particle monitors, intensified, but so far, none has been able to provide the missing piece of this cosmic puzzle. The period of immobility also offers a unique window to investigate the internal structure of 3I/Atlas. The brightness stability during the 48 hours suggests the object didn't suffer catastrophic fragmentation, but small structural changes, such as microfractures, internal collapses, or material redistributions, could have occurred without being directly observable. Some experts speculate about the possibility of a microscopic collision with high-energy particles or small fragments of space rock, events that wouldn't leave obvious optical traces but could momentarily alter the body's dynamic state. Others consider that the freeze might be related to still unknown physical properties of these interstellar travelers, perhaps a heterogeneous internal composition, layers of volatile materials in unstable configurations, or even macroscopic quantum effects in extreme vacuum environments. Each minute of those 48 hours represents an opportunity to learn something completely new about the nature of these objects. And then, as abruptly as it stopped, 3I/Atlas began moving again. On Monday afternoon, the first signs of displacement were detected. Within hours, the object resumed an apparently normal trajectory, although subtle deviations from the predicted route before the stop are being analyzed. Monitoring is now continuous and intensified. Observatories keep their instruments fixed on the object, searching for any sign that a new event might occur. Minimal variations in brightness, changes in rotation velocity, shifts in spectral emission, everything is being recorded and compared with updated models. The big question remains: was this an isolated event or the prelude to something bigger? If 3I/Atlas enters a state of immobility again, we'll have confirmation that we're facing a recurring phenomenon, something that could redefine our understanding of interstellar object dynamics. For those following the development of this story, the recommendation is clear. Keep your eyes on the technical bulletins from major observatories. The next chapter of this cosmic mystery may be just hours away. The 3I/Atlas case also raises fundamental questions about the limits of our astronomical prediction capability. For decades, we believed that the laws of celestial mechanics were robust enough to explain the behavior of any body moving through space. Now, a single object challenges that confidence. Scientists from institutions like the Max Planck Institute in Germany and the European Southern Observatory have begun questioning whether our computational models capture the full complexity of forces acting on interstellar visitors. After all, these bodies have traveled for millions of years through environments we don't know, exposed to radiation, magnetic fields, and extreme conditions that may have altered their structure in ways we can't yet measure. 3I/Atlas may be showing us that there are completely new astrophysical phenomena waiting to be discovered. Meanwhile, the amateur astronomy community has also sprung into action. Dozens of independent observers around the world began pointing their telescopes at the region of sky where the object is located. Online forums exploded with technical discussions, image analyses, and attempts to correlate available data. This spontaneous mobilization has been crucial to complement professional observations, especially at times when large telescopes need to be redirected to other targets. Some of these observers have already reported additional small anomalies, brief oscillations in brightness, subtle color changes, that still await official confirmation. What began as an astronomical event restricted to scientific circles has transformed into a global citizen science phenomenon, with thousands of people contributing to document every aspect of this developing mystery. The international scientific press also reacted quickly to the event. Articles in specialized journals are beginning to be submitted for accelerated publication, and several teams have already announced they're preparing detailed studies on the 48 hours of immobility. The consensus among editors of these journals is that we're facing one of the most intriguing astronomical events in recent years, comparable in scientific importance to the first detections of Oumuamua and 2I/Borisov. The difference is that this time, we have an unprecedented amount of high-quality data collected simultaneously by multiple instruments around the planet. This wealth of information may finally allow the scientific community to decipher not only what happened to 3I/Atlas, but also what it reveals about the fundamental nature of objects that cross our solar system from the depths of interstellar space. There are also important practical implications in this event. If interstellar objects can exhibit such unpredictable behaviors, this directly affects our plans for future space missions intending to intercept or study these cosmic visitors up close. Space agencies had already begun developing rapid response probe concepts, capable of being launched within weeks to reach interstellar objects before they leave the solar system. But if these bodies can simply stop, change trajectory, or exhibit other anomalous behaviors, all mission planning needs to be rethought. Engineers and scientists now discuss the need for more flexible propulsion systems, more sophisticated autonomous navigation algorithms, and scientific instruments capable of operating in completely unexpected scenarios. 3I/Atlas may have just taught humanity a humbling lesson. The universe still holds secrets our technology has barely begun to unravel.